Renewable energy has a rising demand in urban areas, and wind energy is one, but they mainly generated in rural areas and coastlines. Facing long-distance transmission and transportation problems, high-rise buildings offer abundant wind resources, makes wind turbine installation in cities appealing. But the turbulence wind in urban canopy layer reduce the horizontal wind turbine's efficiency. Besides, problems like health, noise, vibration and cost also reduce acceptability of HAWT in city. Our project focuses on the effective integration of vertical axis wind turbines into high-rise buildings by applying flow augmentation theory, a novel concept for VAWT integration. To boost power output, it's essential to increase the wind velocity at the inlet and create a negative pressure zone at the outlet. Implementing a separator generates a negative pressure zone, while wedges can enhance wind speed at the turbine inlet. Limited research on this integration makes study on optimizing turbines' geometry to improve efficiency crucial. Design iterations were based on the theory and CFD simulations to enhance the performance. This included adjustments to model configurations, blade design, inlet length, inner shroud, separator length and wedge design. To evaluate the model's performance and identify the optimal turbine design, we conducted outdoor testing to assess improvements in the VAWT with flow augmentation. These outdoor tests were crucial for making informed decisions based on real-world data analysis. Collected data included inlet wind speed and the rotor speed to determine turbine efficiency, also the axial accelerations to observe the structural vibrations. More tests conducted to identify noise sources from the turbine that could impact health and the environment. Our final product is iterated from the tested results, combining features that deliver the optimal performances while validating the reliability of flow augmentation theory. The optimal design included features such as two 20 cm long back separators, curved blades design, wedge with 45°, and two inner shrouds. Our test results showed a 3.1 times performance increase in the optimal turbine compared to the benchmark. In general, conventional wind turbine has only efficiency of 30 to 50%, whereas our turbine are able to achieve up to 62% of efficiency. Also, our turbine produces a sound power level of 67.6 dBA, is within the acceptable noise range. We conducted a feasibility study for a larger turbine at Building 54, based on historical wind data and dimensions, which could supply up to 25% of the university's electricity needs, reducing CO2 emissions and saving costs. To summarize, we developed a novel vertical axis wind turbine, VAWT, with a 12-watt prototype achieving 62% efficiency, and conducted a feasibility study for a 57 kW building integrated system, estimating 500 megawatt-hour annual generation, covering 25% of energy needs and saving 135K a year.